Hello everyone and welcome to topic 6 of deep learning course. So far in this lecture we only talk about the 2D convolutional operation. In this lecture we are going to learn other type of convolutions such as 1D CNN and also 3D CNN. 1D convolution is used when our dataset is represented by one-dimensional array or one-dimensional tensor. Example application is for natural language processing task. Since tasks in this domain use text as an input and text has a pattern along single spatial dimensions such as time, 1D convolutions are great fit. We can use them as more efficient alternative to traditional recurrent neural networks such as LSTM and GROUP. Here, unlike RNN, they can be run in parallel for fast computation. Another domain that benefits from 1D convolution is time series modeling and time series analysis. As before, we have a single spatial dimension on our input data, for example, time, and we want to pick a pattern over a period of time. We can also call this type of the data sequential because it can be viewed as a sequence of values. And the spatial dimension we often call temporal dimension. Here, the data consists of tensor with the shape of depths and different dimension. Here, the depths also can be equal 1 or bigger than 1. We have like a single channel input when we have a univariate time series, such as development of a single stock price over time, or we have a multi-channel input when we have a multivariate time series data. For example, movement data measured with multiple sensors for human activity recognition, or weather forecasting with the two elements of the temperature and humidity. We have multi-channel input when text encoded as a character level one-hot vector. Here, example can bioinformatic data. Imagine we have a sequence genome data set where it's composed of the only four character of TCGA. In this case, we have, for example, four channel input. Similar to a 2D convolution, here we convolve the data with 1D kernel or 1D filter. To calculate 1D convolution by hand, we slide our kernel over the input and then calculate the element-wise multiplication and sum them up. For example, given input size of 1 in 12 and filter size of 1 in 1, by moving the kernel on an input different spatial location, we create the feature map. To create the first entry of our feature map, we need to do a multiplication of 9 times 6, which is like 54 for the first entry, and then go over the input array. And then for the last one, for example, is 6 times 4, which is 24. And this is the last entry of our feature map. Here is our step size is equal 1. Having a filter size bigger than 1, we need to calculate the element-wise multiplications and sum them up. For example, in this case, with a similar input size and having the kernel size of 1 in 2, we need to calculate, first of all, 9 times 3 plus 7 times 6 in order to create the first entry of our feature map. And for the rest is also similar to this. We have the stride of 1 in this example. And another thing is like, for example, the last element also created like this, 4 times 6 plus 8 times 3, which is like 24 plus 24 is equal to 48. Here is another example of 1D convolution where the depth of the input is equal 3. We have the movement data which measured by multiple sensors, and here the task is human activity recognition. We have the three different values for the accelerometer of the X, Y, and Z, where we use them as an input for our 1D convolution, but for the with the like considering three input channel. pass them to the a network composed of the, for example, pooling and also different components. And at the end, we have the loss function for example, in this case, our activity which we would like to classify is jump or run. We have like a two at the end, two classes. Here is also another application of one-way convolution for time series data analysis. The input layer takes the time series and then it passes to the different convolutional layer. We also have a global average pooling in this example. Is one simple example of the time series classification and network architecture. 1D convolutions also have an interesting application in natural language processing tasks. One example is sentiment analysis. Sentiment analysis is contextual mining of text which identifies and extracts subjective information in source material and helping a business to understand the social sentiment of their brand, product, or service while monitoring online conversations. Here, indeed, we do text classification, where for incoming message we predict positive, negative, or neutral label. To this end, we need to create a one-hot vector. Here we use a given alphabet to encode the text review. For example, here we have a sentence of dummy review. Each character is transformed into a one-hot vector, where the vector for the character of D contains only zeros at all positions except the fourth position, as you can see here. The max Each character is transformed into a one-hot vector, where the vector for the character of D contains only zeros at all positions except the fourth position, as you can see here. The maximum length of each review is set to 1014, where the shorter texts are padded with a space of the zero vector, and the longer texts are simply cut. Here, the data is represented as a 1D signal, where the depth is equal to size of alphabet that we have. As you can see here, we have the alphabet in the x-axis, and our y-axis is like the sentence or temporal dimension. Here our kernel are shown by blue, and we use the 1D kernel and it convolves the input into the temporal y dimension, and we will have at the end 1D feature vector. For certain application, 1D CNN are advantages and thus preferable to the 2D CNN in dealing with one-dimensional data such as time series data. Like forward propagation and backward propagation in 1D CNN require simple array operation. However, for 2D CNN, we need matrix operation. This means that computational complexity of 1D CNN is significantly lower than 2D CNN. Another advantage is like training a network composed of 1D convolution is easier. One deconvolution with a small number of hidden layer and hidden neurons, all able to learn challenging tasks. Therefore, we have a shallow network, which training of the shallow network obviously is easier than a deep network because 2D CNN needs to be deeper architecture and more hyperparameter. Another thing is usually training deep 2D CNN require a special hardware setup, such as cloud computing or like GPU cluster. On the other hand, any CPU implementation over a standard computer is feasible and also it's relatively fast for training compact 1D CNN with a few like hidden layer and neurons. Another thing is like because of their low computational requirement, like having a network architecture composed of the compact 1D CNN are well suited for real-time analysis and low-cost applications such as mobile or like handheld devices. 2D CNNs are the most popular type of convolution which used widely in computer vision and image processing. The 2D convolution is a simple operation where we start with a small kernel or filter, which is simply a small matrix of weight. This kernel slides over the two-dimensional input data, performing an element-wise multiplication with the part of the input it is currently on, then summing up the result into a single output pixel. As you can see in this figure, the kernel repeats this process for every location it slides over and converting two-dimensional matrix of input into another two-dimensional matrix of feature or output feature. Note that the size of the kernel directly determines how many input feature get combined in a production of the new output feature. Input size is 5 in 5, and by moving filter size of 2, we will create the feature map of 4 in 4. And for doing this, we need to apply the convolutional operation in 16 different positions. Let's see 2D convolution in one example. Here we have the input size of a 3 in 3 showing in a yellow color, and we have filter size of 2, which is a small matrix of base. By moving this filter to the first spatial location of feature map, which is 3. After element-wise multiplication, here we sum up everything, and then the output of the first spatial location is the first output for the feature. By continuing and moving the kernel to the second spatial location, we can create the output for the next element of our feature map. Here is, for example, 4. Here the stride is 1 and we do not use any padding for this operation. Again, similarly, by moving to moving this our kernel to the third spatial location, we can create the third entity of our feature map, and similarly for the last one. And in this part, we review 3D CNN and their application in the real world. We use 3D convolution when our data can be represented in three-dimensional tensor data. Here, the data consists of the tensor with the shape of, first of all, depth, and the x dimension, y dimension, and z dimension. The dimensions can be both temporal or spatial. Spatial examples are like a 3D imaging data, such as magnetic resonance imaging or MRI, which is widely used for examining the brain, spinal cord, and also like other organs as well. A computerized tomography or CT scan is also another example of 3D data, which is created by combining a series of X-ray images taken from different angles around the body. Here we can use Conv3D for diseases classification or tumor segmentation on the top of the medical images. Another example application of 3D CNN is for like analysis of temporal data, such as videos. Like the videos are a sequence of image frames together. In this case, we apply convolutional 3D on the videos to extract the spatial features. Example application for the video is like human activity recognition based on the feature extracted from the video data. In this case, we move a three-dimensional kernel in 3 directions of X, Y, and Z to capture all important information. In this figure, in the right side, you can see the illustration of the depth of one volumetric data. Here is the MRI image from brain, and the task is to semantically segment the tumor area. Automated segmentation of brain tumor from 3D MRI is necessary for the different clinical purposes, such as diagnosis, monitoring, and also treatment planning. Manual annotation or manual segmentation, first of all, needs a really expert doctor, which is expensive and also time consuming. Moreover, it can be inaccurate due to human error. Here, 3D CNN takes the MRI slice in axial, sagittal, and coronal. Here in this example, tumors are segmented using the 3D unit architecture, which composed of the 3D encoder and followed by 3D decoder. Similar to 2D unit, in 3D unit also we have batch normalization and ReLU activation function after each convolution, and also like max pooling, and in a decoder part we have up convolution as well. And at the end we have the loss function. Here in this case they use the 3D dice as a loss function. The goal of action detection is to detect every occurrence of given action within a long video, to localize each detection within a space and time. Deep learning-based approaches have significantly improved the video action recognition performance, especially those methods who are based on the 3D CNN. 3D CNN is able to capture motion characteristics in videos. Here, the network takes the whole frame as a search space with some predefined bounding box templates. In this actually example, the task of the CNN is for the action recognition and also object localization. The schematic of the 3D convolutional neural network, as you can see, we move the kernel, where the kernel is also 3D in three direction of X, Y, and for example here T, to get the output of feature map, which is also 3D. Basic architecture of the CNN stayed the same for either 3D, 1D, or even 2D. Like 3D convolution output 3D feature maps, and the feature maps created similar to 2D. It's like a element-wise multiplication. At the end, we have the sum, we have the activation function after convolutional layer, and also the pooling operation here is also in 3D. And these are the references which we use for these slides. Thank you for your attention.